here's an example from the back of the chapter. This is from Hibbeler, and it's chapter 15, number 57. And we've got a block that's on an inclined plane, and we're going to hit that block with a bullet. It's a 10-kilogram block, and it's held at rest on a smooth inclined plane. The bullet's going to be a 10-gram bullet, and it's traveling at 300 meters per second when it becomes embedded in the block. And we wanted to determine the distance that the block will slide up along the inclined plane. So a couple of things that we want to look at. One, you might want to go back and review your ballistic pendulum problem from general physics, because this is very, very similar. We're going to use our momentum to get us part way, and then we're going to use conservation of energy to get us the rest of the way. But we're on an inclined plane, which is a little different than what we typically see on that ballistic pendulum. But that ballistic pendulum problem is a really good one to review before you start tackling this one. So let's look at kind of drawing what's happening here. So I've got my 10-kilogram bullet. It's going to hit the 10-gram bullet is going to hit my 10-kilogram block. We've got an angle of 30 degrees, and we know what's going to happen is we're going to get a slide up the plane. And so I'm going to have a normal force to the plane, and I'm going to have the slide up the plane. Now let's also look at how the problem is stated. One is it says it's at rest on a smooth surface. Well, that means we can make the assumption that friction is going to be, we can disregard friction, or friction is not going to impact the problem very much. We also are told that it becomes embedded in the block. That tells us we've got a perfectly inelastic collision or a perfectly plastic collision in the terms that we're using in our book. So, and then the other thing is we want to orient our problem so that it's going to make the best for us. So let's look at this a little bit differently when we come into the problem. So first of all, I'm going to have a velocity parallel to the plane, but I've also got an x velocity because my velocity of my bullet's coming in on the x direction. So I'm going to have to make some adjustments because I'm going to need that velocity component of the bullet along the parallel to the plane or along the plane. So I do have to account for direction. So we still have our momentum before is equal to our momentum after. The block is at rest, so I can disregard that. We know that I'm going to have the total mass after, so I can take into account there. So I'm going to put in the mass of my bullet, the velocity of my bullet parallel to the plane, divided by the total mass of the system, which tells me that when it hits that instant of that collision, the velocity is going to be 0.259 meters per second along the plane. So let's look at how we're going to use conservation of energy. So we're going to look at the total energy before. So let me kind of take care of this. We get the total energy before is going to equal the total energy of the bullet plus the block. Hang on just a second. We'll do it this way. Okay, we'll just make it simpler on ourselves. And then we'll come back in and we'll make this up here. There we go. And we get the potential energy of the bullet and the block at the end, and that's our conservation of energy equation. So I'm going to have the total, or the kinetic energy before is 1/2 mv squared, and that's going to equal the kinetic energy of the bullet and the block at the top, or as far away as it gets, is going to be equal to 0. Because remember, in my ballistic pendulum, when I reach the top of the swing, all that kinetic energy is converted into potential energy, and so that I have that one at the top. So when I do that, that particular term goes to 0, and then I can solve for h. But we want to look at how that works in terms of our coordinate system. H is the height up in the vertical direction. That's not the distance traveled along the inclined plane. So we're going to have to use a trigonometry to solve for d, because that's what we really need to solve this problem, is our d. And we can use that, and we show that d is equal to 0.00684 meters, or 680 or 0.6844 millimeters.